the little silver lining in the delays is we've continued to make progress on all aspects of the technical risk reduction in the telescope. So this is a segment here without any aluminum on it. So you can see through to the segment assembly. So each of these mirrors, in addition to having active control on the edges, you have to keep that mirror stiff. You have to eliminate print through. So we have a somewhat complicated whiffle tree system behind. We've been through all of that. These have been tested numerous times. We've created to the final segment figure several of the more difficult segments. So all of this is well underhand. Third big component of these mirrors is seen over here, is you have to sense, the edge sensors, you have to sense where one mirror is with respect to another to a precision of about 7 nanometers with no drift, in fact, on that time scale. So sensors are designed. We're now thinking about robust supply chains for those more than anything. But this is an environmental chamber where we're doing some, again, lifetime testing and precision testing for these things. So technically, I'm very comfortable with the status of all parts of this project. Here's a 1/4 scale articulated tertiary scale model in China. This is one of the more complicated joints of the telescope structure in Japan. So we've gone through to final design in many of these things, and we're prototyping some of the question mark things and all over the project right now. This, you're not going to read this. This is a chart, a table of the maturity level, technical maturity level of various things. These are big things: enclosure, summit facility, telescope structure, primary mirror. Anything that I circled in red, we're at production fabrication. Anything in blue is in final design. And if I ran through this long table, you'd see lots and lots of red and blue things. So technically, we're ready to go. Okay, this is the same slide that Jim showed. Just to note that all the green ones, here are first light for the 30-meter telescope. And in terms of the US ELT, you'd say, well, I don't know, it's a complementary set of instruments. And it turns out it is by accident, because the two projects developed in parallel but independent to this, as they define first light instrument. But in fact, both have some workhorse instruments, an optical, multi-object spectrograph, and something that works at the diffraction limit of the telescope. And yet we diverted a little bit, just by accident, in a way that does complement some of the first light capabilities of the two telescopes. You don't build, in my opinion, 25-meter or 30-meter telescopes just to collect a lot of light. Even though sometimes having that high photon rate, you can do special things that are hard to do with a 10-meter or an 80-meter telescope. You build it for the diffraction limit. So from the very beginning on both projects, we've designed adaptive optics system that can, in fact, achieve the diffraction limit of the two diameters. We have something in Canada, which we're past final design for, I think, all that. Well, for most of the significant components. And the figure of merit here is wavefront error. So 187 nanometer RMS wavefront error translates to strels of about 0.75 at K. And this is better than, I think, any adaptive optics system currently in operation. So these are hard to build. The challenges of adaptive optics on these large primaries, where you have a whole bunch of ornate circles over that primary, are significant. I think we understand how to deal with that. Okay, so the site. The site selected a decade ago now, 10 years ago, for the TMT was Mauna Kea here. We realized, well, just a second, forgot myself. So the American Astronomical Society, we appreciate the fact that at this meeting held in Hawaii, I think it would have happened. There have been a number of sessions devoted to talking about the challenges of sacred mountaintops, not just Mauna Kea, but all over the world. And astronomy use is a problem that's been building, and we're just, I think, really starting to grapple with it now. And for better or worse, the 30-meter telescope is at the forefront of that grappling. So the AAS has done a really nice job of setting up sessions where people can go and become better educated and also express their opinions. So we appreciate that they did that. So we have also realized in 2009 that there were going to be challenges with putting another telescope at Mauna Kea. So before we took that decision, we spent almost 5 years visiting the Big Island, Oahu, talking to people with the goal of understanding how the 30-meter telescope, another telescope at Mauna Kea, where astronomy had become controversial, how we could not only be accepted, our goal was to be welcomed here. And there was no way that people in California could figure out how to do that properly. We depended on talking to the folks on the Big Island and here in Oahu. And so we did that. We talked and listened for a long time. These are some of the people we talked to. Richard Ha, people in the Native Hawaiian community, Koa Rice. Ed Stevens was the head of the Kahu Kaumana, the Cultural Advisory Committee for Mauna Kea, an absolutely wonderful man. And we learned a huge amount about how to do a project better at Mauna Kea. And those involved minimizing the impact on Mauna Kea, both to the environment and to cultural practices. It meant making sure that there were some associated benefits for the local community. Meant that we used to talk about the coexistence of astronomy and culture at Mauna Kea. That's a really low bar goal, coexistence. We really need a way to integrate the two things so that each is strengthened by the other. So we thought we had learned quite a bit from these folks. We designed a number of programs, and we still have many supporters in the Native Hawaiian community, which sometimes gets lost in the news coverage. So we developed partnerships on the Big Island for STEM education, workforce pipeline development so that local students would have an opportunity to work, accept those good jobs in the university. It's been a very popular program. For the first time, we pay a significant rent, $1 million a year, which is specifically to provide resources for stewardship of Mauna Kea. These are two of the Akamai, is one of our workforce pipeline programs, working, it looks like, in one of the Keck telescopes. Okay, so we also we learned in those listening sessions that the actual location on Mauna Kea is very important. All land is sacred, in fact. All land on Mauna Kea is sacred. But there are some places on the summit ridge that are much more sensitive than other places on the mountain. So the 30-meter telescope location is down here on the 13 North lava plain, which is actually far from the summit ridge area. The actual summit of the mountain has never been built on. So at the 30-meter telescope location, which again was selected after consultation with the cultural advisory groups, you can only see the telescope from 14% of the island. You can't see the telescope. You wouldn't be able to see the 30-meter telescope from the true summit. So minimizing cultural impacts had a lot to do with view planes. So anyway, we got lots of excellent advice and took it. Nevertheless, in 2015, when we started construction, we were stopped by protests. That happened again in 2019, and that's where we are right now. The project is currently stalled. There was an encampment on the road that's been moved this week. But we certainly don't have agreement from everybody in Hawaii that building the 30-meter telescope is a good idea. And if you talk to people, and I spent a week on the Big Island, I went to the camp, I talked to Lyft drivers, I talked to waitresses and waiters in restaurants. You hardly ever hear complaints about astronomy or the telescopes. You very quickly segue into these many ills in the Native Hawaiian community that have built up in some cases for over 100 years. So the TMT has become a symbol and a rallying point for a whole host of things over which we actually have no control. But in fact, we have a lot of sympathy. So TMT, I'm actually a little proud of the fact that we have been a rallying point for many of these things, and I hope that this controversy is the launching point for resolving many of these long-standing Native Hawaiian issues. So people often ask, well, are you talking to them? The answer is yes. Many of these conversations are much better done in a quiet way with little publicity. So those conversations, many conversations are actually underway, like this with TMT and some of the protest leaders, but at the state level, with the governor, with many influential people in the community. So that's going on. If this is going to be resolved peacefully, and the most important thing I'm going to say is this, the TIO board and the members above us, the corporation, we're committed to Mauna Kea with peaceful access. We don't want to go up in the wake of police If that's going to happen, that can't just be the TNT, because many of these issues are just far out of our control. So that's why it's important that we work in concert with the many other people interested in the future of Hawaii. So that's going on. And just to remind people, we really have a lot of folks who are strongly in support in the Native Hawaiian community of the 30-meter telescope, and it's partly because of the economic value. These been very good jobs at the Big Island. But it's also, there are lots of people who believe that astronomy is a natural continuation of the Native Hawaiian cultural uses of the sky and Mauna Kea. So we have supporters of it. Okay, even though I'm out of time, I'm going to talk one more minute. In 2016, after we did not gain access to Mauna Kea on 3 different tribes, we realized that it would be prudent to have a plan B. The Northern Hemisphere was a priority for us, so that kind of limited us to San Pedro Martir in Baja California, and the observatory at La Palma, which is one of the Canary Islands. So this is La Palma. There's the
GTC.
Yeah, it's the other telescope, the GTC. This is the site where the TMT would be on the mountain there. We spent a bunch of time evaluating the specific sites where we might build the telescope. It turns out you don't easily say, okay, we're going to just move from here to there, because you have different seismic activity levels in this place, the frequencies are different, the ground is different. It's a significant and somewhat expensive effort to say, what would the 30-meter telescope look like moved from Mauna Kea to ORM? But we've done all of that, and we went through a permitting process. So as of December of last year, just a month ago, we have all the permits in place to build it in La Palma if that decision gets made. And like I said, we wanted to build in the Northern Hemisphere, and it's interesting why we chose that site. So this is the comparison. My next slide will address that last point. The main difference is ORM is significantly lower in elevation, which means mean temperature is warmer, there's more atmosphere above you, so precipitable water is higher. And I think the consequences of that are, compared to Mauna Kea, the TMT would have some losses of efficiency of performance, now it's 1.5 microns. Doesn't mean you don't do that work. It means you do it, and it takes 20% longer or 30% longer. At short wavelengths, there's higher extinction simply because you have larger intermass repeated at all times. So short of 400 nanometers, you have a little bit reduction in efficiency. But when we look through all the numbers, and got our own numbers, ORM is an excellent site, despite the reputation that's out there with some astronomers. So, but what really made a difference is this. So these days, you can measure the integrated scene of the atmosphere above your site at the height of your primary mirror. And that's an interesting number. But of course, we build these telescopes to work at the diffraction limit of the primary mirror. So what counts even more is if you measure the turbulence profile above the site, you run that through your adaptive optics simulator or your system in the future, and you see where you can do better correction, which has to do with the coherence time. And in this particular case, it happens to do with how well distributed the turbulence is above your site. So these kind of too complicated to show. This is residual wavefront error, so bigger is worse. The blue line and the black line are Mauna Kea and ORM. The green line is Amazonas, where the EELT performed, where we tested for many years. So it's a more complicated turbulence profile of Amazonas. In fact, many of the excellent mountains where we have telescopes. So the real reason I think in the end we chose La Palma was because of this favorable turbulence profile to allow us to do excellent adaptive optics correction. Okay, so I ran a little long. The last thing I really wanted to say, similar slide to Jim's last slide, is a really important thing that is perhaps overlooked sometimes, is to build a $1.5 billion complex technical project with a complex partnership. You really have to have an outstanding team, and we do. So one of the things that we built, in addition to retiring all these technical risks, is we really have some folks who are extraordinarily good at managing all over the world now these very complicated technical activities. So I'm proud of this team, and many of them are here, and I wanted to make sure they knew that we were proud of them. That's an extremely important asset to have. Okay, so let me see, anything new here? Just in case anybody doubts it, we're 100% behind the US ELT. We need to resolve the site on a time scale that I think is such that, ASTRO 2020 knows what to recommend. I mean, they're not sure exactly what our telescope looks like because we're still not sure what's going to do it. I think that's makes it difficult to give a favorable recommendation. And it doesn't matter where we go, ORM, Mauna Kea, this will be an incredible facility. And it'll complement beautifully the incredible facility that we're talking about. Thanks. Sorry about that.